SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering basic and applied, and today we shall discuss about several parameters. Those are directly related to the performance of the internal combustion engine. If we recall, in the last class we have talked about the mean effective pressure, and we have seen that mean effective pressure is an important parameter for the comparison of engine performance, and we had seen that when work output is expressed, then the concept of mean effective pressure is very useful, and from there we could write several forms of mean effective pressure considering different works. So, if we discuss about the mean effective pressure that we had written in the last class, mean effective pressure, that is, as such, if we write the expression of work done again, integral P dV, and for the multi-cylinder engine, as we had also discussed that very often engines are multi-cylinder. So, it is always convenient to write the expression per unit mass of the gas in the combustion chamber. So, this is W, small w, and we can write P small dV, and we had seen that the pressure inside the cylinder is continuously changing. So, though it is the differential volume dV, so that is the displacement by the piston. So, what would be the work done being impressed on the piston, be it the work which is available inside the cylinder or be it the work which is available at the crankshaft. So, P is very difficult to calculate because it is changing continuously with time. Also, there is a spatial variation of pressure. So, what we could write in the last class, that W is, we can write mean effective pressure or average pressure, that is the concept we are bringing here, and then delta V, and this delta V is basically V T d C minus V B d C. So, that is the change in volume. Okay. So, what we can write from this, mean effective pressure is equal to W divided by delta V. Now, it is not mandatory that we should always write this quantity in terms of the in terms of specific quantities. We also can write like this, W by V d. So, this V d is the displacement volume. Okay. Now, see, today we shall discuss about a few important parameters. Those are directly influences, or those are directly related to the performance measurement. So, you know that why mean effective pressure is important. Mean effective pressure, the concept we are bringing here only to eliminate the issues, or rather only to get rid only to get rid out of this issue, that is the pressure is changing continuously in the combustion chamber. but also this parameter is very important. You know that when we try to compare the engine performance, anything when we try to have a comparison, we must have a common basis. Now, for engine in terms of the design as well as the output, work output, if we compare several engines, we must have a common parameter, and what the common parameter would be for such a case when we are trying to compare the engine performance or even in the engine design. You can tell me that torque may be an important parameter or the power may be an important parameter. So, if we consider torque for as a common parameter for comparing engine in terms of the design as well as output, maybe larger engine always will look better, while if we consider power as the parameter for the comparison of engine performance or engine design, then definitely speed would be higher speed becomes important. But now, if we consider mean effective pressure as a common parameter for comparing or for comparison of engine design and performance, then it becomes convenient. So, mean effective pressure is not only the concept that we are writing here, because that is only to eliminate the spatiotemporal change in pressure that is there always inside the cylinder to get rid out of that issue, but also this parameter is an important parameter for comparing the performance of the engine as well as for comparing the design of the engine instead of torque and power. So, also we had discussed that we could write this mean effective pressure in its different form. So, mean effective pressure we are including B at the the suffix we are writing B. So, if we use suffix B, that is brake mean effective pressure, we also can write indicated mean effective pressure, we also can write frictional mean effective pressure. So, all these three fine. Now, what we could write that the work which is available inside the cylinder is not the work which is there at the crankshaft. Why? Because of several issues, frictional loss as well as the power or work needed to run several devices for the parasitic loads that we have discussed. And we had seen that this indicated mean effective pressure we could write, that is that brake mean effective pressure plus frictional mean effective pressure. So, that means we can write brake mean effective pressure equal to indicated mean effective pressure minus FMEP. Similar to what we had written in the last class, that W brake equal to W indicated minus W friction, and from there we could write that this quantity WB is less than Wi, and we really do not know it is less than Wi by certain amount, but we really do not know what is that amount. So, it is we can write one factor multiplied by Wi, and that factor is known as mechanical efficiency. So, this mechanical efficiency eta m is Wb by Wi, and it is always less than 1, because eta m is always less than 1. Now, today we shall, so this is what we have discussed in the last class and we could write it. So, we had also discussed the indicator diagram in the last class, and we had seen that if we just try to recall the indicator diagram about the atmospheric pressure line, there are two different loops. The upper loop that gives us the positive work, and that is the work we are getting, while the lower loop or lower part is the negative work. So, that is the work that we need to supply to the engine cylinder. So, the net work that we will get is that positive minus negative. So, now issue is that is what we can get from the indicator diagram. So, if someone would like to calculate what is the work output from the engine, he or she needs to draw the indicator diagram, and from there he or she can calculate the net work available from the engine. But this is very difficult always. Instead what is done, some parameters are introduced to measure the work which is available at the crankshaft. So, today we shall discuss about what that parameter is. Now, if we write an important parameter that you all have studied, that is torque. Torque tau. So, what is torque that you have studied in mechanics course? So, this is basically an indicator. As such, I should say torque is a good indicator of an engine's capability or ability to do work. So, let me repeat it. Torque is a good indicator of an engine's ability to do work, and it is defined that you have studied in mechanics course, that is the force acting at a moment distance, and this torque is related to the work. So, if we write the expression of torque is tau, then it is related to the work with this expression. Now, you may ask me a question, why we are writing brake work? So, as I said you few minutes back that if someone would like to calculate or measure the work output from the engine, definitely he or she must be taking an effort to draw the indicator diagram, but it is not a practical viable case. So, we need to go for another we need to go for several other rather we need to look for other options from which we can calculate the work output. So, basically if we can measure torque, since this torque is related to the work, then if we can measure torque, then we can get a fair estimate about the work that is being produced. And question is why it is brake? You have I think studied about the dynamometer. So, basically dynamometer are used to measure some quantity, and that dynamometer measures that quantity at the crankshaft. What we had seen in what we have discussed in the last class, the work which is available at the crankshaft is the brake work, right. So, since the dynamometer can only measure the quantity torque at the crankshaft, so definitely that torque can be related with the work which is available at the crankshaft, and that is why it is brake work. So, I had written that torque which is defined as the force acting at a moment distance and which can be related to the work through this relation, but I have used this suffix B. So, that is the brake work. Why it is brake work? Because dynamometer which would be used to measure torque at the crankshaft, where only brake work is available. So, we can write this is brake work. So, in the last slide I have used this is not suffix, rather it is prefix. So, B prefixes B, I and F, these are used to indicate several quantities, several mean effective pressures, but again it is brake mean effective pressure, this prefix I is used to denote this indicated mean effective pressure, and this is friction. Okay. So, now this is WB, and this can be written further. So, this is brake mean effective pressure into Vd divided by N. Note it, because we are writing not in specific form. So, WB brake work, and if we look at the expression, If it is W brake, then B MEP, and that it would be VD, displacement volume. So, that is what we have written, brake mean effective pressure VD divided by N. This small n is introduced here, that is number of revolutions per cycle, right. So, this is how this is the expression of torque. So, you can write this torque tau will be equal to brake mean effective pressure 1 upon 2 pi into VD divided by N. This would be very useful to calculate numerical problem. This N is 1 for 2 stroke cycles engine, this is equal to 2 for 4 stroke cycles engine. Okay. Because for the 4 stroke cycle engines, we have seen there are 2 revolutions per cycle of the crankshaft. So, this is that of the crank, and what we can write N equal to 1 for the 2 stroke. If it is 4 stroke, that would be 1 upon 4 pi brake mean effective pressure into VD. Okay. So, this is what we have written. Now, question is that why brake mean effective pressure and why brake work, that we have already discussed. Next is again another important parameter which will be mostly used to compare the engine performance, that is power, right. So, if we can calculate work done by measuring torque. So, dynamometer which is used to measure torque, which is connected to the shaft of the engine, from there we can get what would be the power, what would be the work output. If we know the work, then what is power, that is P, and that is rate of work output, right, and this is the rate of work output, and instead of writing P, let me write here. So, power is rate of work output, the word rate I am using. So, we can write this is W dot. So, this is W dot. So, this is W into capital N by small n, where capital N is engine speed and small n is already I have written number of revolutions per cycle. Okay. So, that is W n upon n, and we also can write in different form, that is 2 pi T tau into n, that is in terms of torque, because essentially we are writing rate of work output. So, if we can write in terms of torque, then we can write like this. Okay. Now, it is very important that what would it be if we try to express this power in terms of brake mean effective pressure, then what would be the expression. So, that is 1 upon 2 n brake mean effective pressure 2 n or 2 pi or 2 n into VD. So, VD I am writing AP into UP, average of course. This is very simple, just some algebraic manipulation. So, 1 upon 2 n brake mean effective pressure into AP into UP, that is AP is the piston area and UP is the average piston speed. So, that will give the displacement volume. Okay. So, because we are trying to express this quantity in the rate form, that is with change in time, then the AP into UP, that is displacement volume. So, you know change of the rate of change of the volume. So, you know that so these are the several forms of the power. So, we can also calculate power. Now, issue is we have expressed the form of torque, power, and all these are very important to calculate the or to determine the engine performance. So, when we are talking about engine performance, you know that we are getting something at the cost of something else. So, we are getting work output at the cost of some input energy. So, definitely though we are trying to calculate work output or power by using all these expressions, definitely we need to measure the torque which is available at the crankshaft using a dynamometer, but those these amounts these quantities are measured and we can predict, but when we are trying to compare the performance, we again need to look at the input energy. So, basically this is the amount of work which we are getting from the engine at the cost of what. So, basically we also need to look at what are the input energy, what are the different, rather what is the input energy to the engine, and to express that we also need to define a few parameters. What are those? We have already discussed about the mass flow rate of fuel and mass flow rate of air, because fuel alone cannot be used to run engine. So, for the transportation vehicles fuel itself cannot ensure that the combustion will be completed. So, we had seen that we also need to supply adequate amount of air. So, we have discussed about air fuel ratio. So, that is air fuel ratio. So, that is m dot A or m dot F, kg of air by kg of fuel, or we can write mass flow rate of air by mass flow rate of fuel. So, we can write either in this rate form or only in the just mass kg of air and kg of fuel which is being supplied. So, this is very important because fuel alone cannot ensure that the combustion will take place or combustion will be completed. So, we need to supply adequate amount of air as well. So, what would be fuel air ratio? So, that is 1 upon F, that I am not going to write. Now, issue is why I am trying to discuss all these parameters, because as I told you that we can get work output from an engine, and that amount of work is obtained at the cost of some input energy. And if we, what is that input energy? Because you are supplying fuel. So, the chemical energy that is remaining stored within the fuel, that will be utilized to get the mechanical energy, right, that is what we are getting. So, what is the amount of fuel to be supplied to the engine? For that is air fuel ratio, and we have seen that there is a perfect chemically correct air fuel ratio, that is the stoichiometric air fuel ratio. So, if we write this air fuel ratio stoichiometric, and so this is the air fuel ratio stoichiometric. So, for a given engine, if we can supply air fuel ratio stoichiometric, we will be getting, we can ensure that the combustion will be completed efficiently, and we will be getting some work output. Issue is there will be several, rather always in most of the time transportation vehicle will not run in its design condition. So, either maybe we need to go for power zone, that is deviation from the cruising zone, also depending on the weather condition. the air fuel ratio that would be required to run the engine at that condition would be somewhat different than the air fuel ratio stoichiometric. So, depending on the situation whether we need to run engine in the power zone or if we need to run the engine in a space where ambient temperature, ambient conditions are not same, then the air fuel ratio that would be required to run the engine at that prevailing condition will not be equal to the air fuel ratio stoichiometric. So, this air fuel ratio actual will be somehow different than the air fuel ratio stoichiometric. Now, what is the deviation? So, this ratio of these two quantities is also known as equivalence ratio phi. So, this phi is equivalence ratio. So, the significance of this ratio is that this ratio gives us a clue about the deviation of the air fuel ratio from its stoichiometric quantities. So, basically the actual air fuel ratio that is needed to run the engine at any condition from its stoichiometric condition is obtained by knowing the equivalence ratio, because all these quantities are related to the performance of the internal combustion engine. So, this is the equivalence ratio. Now, another important quantity which is very often used is known as specific fuel consumption. So, let me write in the next slide. So, that is or SFC. What is specific fuel consumption? So, basically you know that this is something this is the parameter, again rather performance analysis parameter. It is defined as the mass flow rate of fuel divided by W dot B. So, that is a brake work. Now, if it is, see, I have intentionally written brake, it is not mandatory that it should be always brake. So, if I remove why I had written brake, because you know eventually the work we are getting from the engine is the brake work. So, the amount of fuel that we are supplying, though the actual amount of work will be produced inside the cylinder is higher than this brake, but we are actually getting WB. Okay. So, let us now remove this B. So, this is W, and if we write it, so this is W, that is rate of work, that is power, and that is mass flow rate of fuel, right. So, this is the generic form. Now, again if we use the prefix B, SFC, so we will be writing m dot F divided by W dot B, while if we write ISFC, indicated specific fuel consumption, that is m dot F divided by W dot B, W dot I. So, this is W dot I. So, if it is, if we are looking at the brake power, then it would be brake specific fuel consumption, while if we look at the indicated power, then it would be indicated fuel consumption. Why it is so? Now, let me tell you, you know that if we just look at, or if we can measure only the brake work, then again we will be considering the brake fuel specific consumption, because we are getting brake work, and to calculate the brake work, I mean we are getting brake work, but for the calculation if we consider indicated work, then the fuel consumption would be something else, because this is much more higher than WB. So, if we consider indicated work or indicated power, then specific fuel consumption would be less. So, we cannot say that a engine or any transportation vehicle which is having lesser specific fuel consumption and would be giving this much amount of work. So, if we say, then we have to say correctly that if that is the amount of work which is available at the brake, then brake specific fuel consumption will be little higher. So, we cannot say the brake work which would be the work which would be available at the crankshaft at the cost of the indicated specific fuel consumption, because the specific fuel consumption considering brake work should be little higher than the specific fuel consumption obtained using the indicated work. Okay. So, again it is similar to what we have discussed, like brake mean effective pressure and indicated mean effective pressure. So, we can write it. We have seen that if we write it, that mechanical efficiency, we will be discussing about several other efficiencies of internal combustion engine in one of the next classes. So, mechanical efficiency we could define like brake work divided by indicated work. So, we also can write in the rate form W dot B by W dot I, right. So, can't we write like this, m dot F by W dot I divided by m dot F by W dot B, and if we like, so just we are rearranging. Why we are doing so? You know, if we write like this, then we can write mechanical efficiency. So, this is the mechanical efficiency. Okay. So, that is m dot F by W dot I. What is this? Indicated specific fuel consumption. So, we can write ISFC divided by BSFC. So, again we could write mechanical efficiency in terms of the specific fuel consumption. So, you can see that the indicated specific fuel consumption is always less than the brake specific fuel consumption. Okay. So, what we have discussed today, that is the torque and brake specific fuel consumption, and if we just try to plot, and also the power, you know. So, if we try to plot all these quantities with engine speed. So, this is speed, say this is specific fuel consumption, it is like this. Then if we plot speed versus specific fuel consumption, then torque tau, that is speed, then we also can plot speed versus power. Okay. So, we can plot speed versus power, speed versus torque, that is horsepower, whatever the unit. So, this is let me go back to the slide wherein we have written the expression of torque and power. So, this is the power, you can see that if we can measure torque, we can get the expression of power, and this is the torque. So, all these are related to the engine speed. So, if we write this is power, so power is like this, right. So, this is the variation of power, this is the variation of specific fuel consumption, then what would be the variation of torque? Can you predict by knowing the specific fuel consumption and power? So, this would be just reverse of the specific fuel consumption. Okay. So, we had we could establish the expression of speed, specific fuel consumption, torque and power, and if we can plot, rather if we try to plot these three quantities with a change in engine speed, the variations will look like this. So, issue is why the variations are like this. If we increase speed, SFC decreases, reaches at its minimum and then again increases, while it is also, if we increase speed, torque increases and then finally becomes maximum and again for decreases. So, the nature of all these curves, the physical reasoning behind the nature of these curves we will explain when we shall solve any numerical problem, whether it is for CI engine or SI engine. So, now today let us solve one numerical problem which will, if we solve one numerical problem, that will give us confidence to solve several other problems. So, the problem statement is a 4-stroke cycle SI engine operating at 3600 rpm and power distribution measured by the dynamometer is 65 kilowatt. The engine has a total displacement volume of 2.2 liters and has mechanical efficiency of 85% at the operating rpm. The dynamometer has an efficiency of 95%. We need to calculate power loss due to friction in the engine, brake mean effective pressure, engine torque and engine specific volume. So, whatever we have discussed in today's class, just by considering this numerical example, if we solve it, that will give us enough confidence to solve several other numerical problems, and at least that will help us to understand the concept that we have discussed. Okay. So, let us solve it. So, you know that brake power, dynamometer, as I told you, the dynamometer is used to measure the dissipation. So, basically the torque which is produced when the shaft is rotating, right. So, brake power we can write WB, right, WB dot, that is 65 kilowatt divided by 0.95. So, this is kilowatt, this is kilowatt. Okay. So, I am not going to write, because brake power we can calculate easily, that is WB dot, that is 65 kilowatt, that is the dissipation measured by the dynamometer divided by 0.95, because dynamometer itself efficiency of 95%. So, dynamometer is not 100% efficient. Next, what we can do, what would be indicated power? We also can calculate indicated power. W dot I equal to W dot B divided by eta mechanical. So, if we know the mechanical efficiency, so that would be 65 divided by 0.95 into 1 upon 0.85. So, this is the indicated power. I am not going to calculate, because you can easily calculate what would be the numerical value. So, this is, so if we can calculate brake power, if we know the mechanical efficiency, and we have defined this, that mechanical efficiency is nothing but the ratio of brake power to the indicated power. So, from there we can get it. So, power loss due to friction in the engine. So, if we just focus on this particular point A, so A, power loss due to friction, that is what is W dot F equal to W dot I minus W dot B. Since we can easily calculate W dot I and W dot B from this, we also can calculate W dot F. So, you can calculate it. So, this is 65 divided by 0.95 1 upon 0.85 minus 1, right. So, this is the loss. Okay. So, power loss due to friction. Okay. If we go to the next slide, so break mean effective pressure, that is what, just by using WB divided by VD, right. So, mean effective pressure into VD equal to work done. So, if we use prefix B, that would be break work, that is what we have discussed in today's class. So, we can write it, you know, that WB dot by, right, this quantities divided by VD, where N by N (3600 rpm by 60 revolution per second by 2 revolution per second, right, because it is 4 stroke cycle, it is 4 stroke cycle SI engine. So, small n is 2, there are 2 revolution of the there are 2 revolution per cycle. So, small n is equal to 2. So, that is why we have written 2. So, 3600 by 60 revolution per second by 2. So, we are getting n by n. So, we can write WB to WB dot by n by n. So, that is just you know very well. So, we can get it from there, and VD equal to 2.2 liters. So, that is 2.2 into 10 power minus 3 meter cube per cycle. So, basically per cycle the displacement volume is 2, per cycle displacement volume is 2.2 liters. Okay. So, if we calculate it, this is the unit would be kilopascal. Okay. Now, what this is B, and if we go back to the problem statement, so we have calculated brake mean effective pressure. What about engine torque, that is C? Today we have discussed about engine torque 2 pi, if it is tau, that can be written in terms of work, that is W B, and if we write n, then W B dot. So, we can write this is W B dot. We had seen today that torque, torque tau is related to work, that is 2 pi tau is equal to W B, because we are trying to write in the rate form, that is powers, and 2 pi tau n. So, now what would be the torque? Tau would be equal to W B divided by twice pi n. We know all other quantities, right. We can easily calculate, because n equal to 3600 by 60 revolution per second. So, we can easily calculate, and we have already, so this is, that should be equal to, so W B dot equal to 65 divided by 0.95 into 1 upon twice pi 3600 by 60, that you can calculate. And what would be the unit? So, you also need to write the unit properly, otherwise you will not get credit. Okay. And finally, we need to calculate the engine specific speed. So, engine torque is also done. So, we are left with engine specific volume. So, now if we go back to the previous slide, D engine specific volume, okay. And if SV, that is Vd divided by Wb dot. So, it would be twice 2.2 liter divided by 65 divided by 0.95 kilowatt. So, that is liter per kilowatt. So, this is engine specific volume. Okay. So, basically what is the what would be engine specific volume? You know that perhaps this is first time I am introducing this term. So, per kilowatt, what is the displacement volume needed? So, that is the specific engine specific volume. So, 2.2 liter divided by, because essentially this is the brake work again, because I did not write W dot I, because the work which would be obtained from the engine is the brake work. So, per kilowatt of that brake work, what is the requirement of the kind of displacement volume. So, that is the engine specific volume. So, to summarize today's discussion, we have discussed about several parameters, those are directly related to the engine performance, those are very often used to measure the performance of the internal combustion engine. We have tried to express their mathematical forms, and finally, we have tried to express their variation with a change in speed, though we did not discuss about the nature of the curve, and that part we will discuss in one of the next classes. And finally, we have solved one numerical problems, and by solving that problem we have understood how we can calculate several performance measuring parameters knowing certain information or knowing certain things of the internal combustion engine. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.